Hello everyone. So this is a ninth lecture on special theory of relativity. So in our previous lectures we discussed about Lorentz transformations, and in earlier lectures we discussed about principle of relativity in restricted sense. So today in this lecture we'll discuss about relativity of simultaneity of events and applications of relativity. We like time dilation and contraction, so on and on. Okay. And this is your second last lecture on special theory of relativity. The last lecture will be on introduction to 4D coordinate system. Okay, so let's start this particular segment today. So this is fixed, you can see. Now, first of all, our today's first topic is the relativity of simultaneity of events. What is the actual meaning of event? We will discuss in next lecture, but just for a brief, since I'm giving you, event is actually called as space-time, means it comes under 4D coordinate system. Okay, but uh, in today's lecture we will just consider about events, whatever events are occurring in the environment, like you say, um, you can say leaves fall from the, you can say, tree. So that is an event. So event is just an, you can say, in the simpler term we say whatever happening in the nature, that is termed as event. But in more, you can say, um, mathematical, or you can say in sense of physics, we discuss about a space-time as an event, as a 4D coordinate system. But in today's lecture we are going to discuss mainly about relativity of simultaneity of events. So what is simultaneity? Simultaneity means occurrence of occurrence of two or more events at the same time. Okay. So two or more events which are occurring at the same time, they are termed as simultaneous event. Okay. Now relativity. Now it is relativity of simultaneity, means events are simultaneous, means they are occurring, one or more events are there which are occurring at a particular time, but actually they are relative. It means in a, say, any one frame, events are simultaneous, but in other frame it is not simultaneous. So that is what it is, the relativity of simultaneity, where we will discuss about that events are simultaneous in one particular frame, and it is showing non simultaneity in the other frame of reference. Okay, so that is our main, you can say, agenda of understanding the relativity of simultaneity of events. Okay, that some events are occurring, some events are simultaneous, same event, the event is same. What is actually happening, that event is, this particular event is same, but in suppose f1 frame, there are two frames, suppose f1 and f2. Wait, let me write it clearly. There are two frames, we have f1 frame and f2 frame, and one event is, the same event is simultaneous here. Now what actually we are saying about simultaneity of event, we'll discuss about it through an example, very famous example. But suppose in frame 2 it is non-simultaneous, so it is possible. That is what actually the topic is, the relativity of simultaneity of events. Okay, and the events also. So let us discuss through an example. We'll consider two frame. One frame will be your uh, ground frame, which is approximately inertial, and we will consider it inertial for the sake of, you can say, convenience. And second frame we will take is, firstly let's name the frames. We take two frames here. Suppose this is f1 frame, we will name it as ground frame, Okay, and this ground frame is approximately taken inertial for our convenience. Okay, now second we will take frame 2, that will be an accelerated frame. Actually you can say train frame, or you say non-inertial frame, or you can in short say accelerated frame. Got it? There are two frames. We are naming two frames. First is ground frame and second one is train frame. You say non-inertial or you say accelerated frame. Okay. So let us discuss about it. So we will use an example. We will use an illustration. That illustration will be that lightning strike strikes at ends of the frame. Little it is, you may feel it vague, but let me clarify you with the example. Okay. So suppose we will take an example. Justly, the illustration is lightning strikes at the ends of frame and how they are reaching to the certain point which we'll define today, means right now, and that we will discuss now. Okay. So suppose this is a ground frame. So this is the ground frame, and we are taking these 2 points. Suppose this is A point, this is B point. Got it? There are 2 points A and B. They are termed as end points of ground frame. Okay. Now there is a point we will assume which is in the midway of this, or you can say at the particularly the perpendicular bisector of this particular, if you are making it a or considering it a line, then the perpendicular bisector of this particular line which bisects it in two equal halves. Now, that particular point is called M. That M is called midpoint. So this midpoint is very important here in our discussions today. Relativity of simultaneity of event. This midpoint plays a very important role because when the lightning strikes here, okay, when you can say lightning strikes here, okay, it strikes at both ends. Okay. Now what we will observe from ground frame, or you say when we are on the ground frame, then what we are observing is that the time taken by lightning to strike, or you can say to reach, actually to reach this particular midpoint from both the ends are seen. When suppose this lightning takes you say t time. Now since it is a lightning, so it will travel with speed of light. That's so obvious. Okay. So suppose we take beside taking this t, okay, let's take something different here to just prove that on this at this particular midpoint the lightning the time taken by lightning to reach from both ends are seen. So we will just consider that this AB is of length suppose 2d. Okay. Now since it is a midpoint, so we will divide it in d and d. Okay. Now lightning is coming with a velocity c. Okay. And since it is coming with a velocity c, and we are just assuming that the time taken by lightning to strike to come from this particular A N to B M, sorry, so the time taken by the lightning uh, from particularly this end to this particular point, that is M, is t. Suppose this time taken is t. T is the time taken. We'll define this particular new terms, and the time taken by lightning to strike from this particular NB to this particular M, let's say it is t dash. Okay, so let us firstly name it. T is equals to time taken by lightning to reach M from A, and T dash is the same to reach M from B. Now we will see our you can see this midpoint. Since this M is at midpoint, so this particular distance are same, so we can write, since you can say AM, actually we write it more clearly that AM is equals to B. Now AM is the distance, so distance is speed into time. So we also observe here that this particularly light of speed of light is c, and time taken here is t, and here it is t dash. So from here you can see that t is equals to t dash. So this tells us that the time taken by lightning to reach particularly to point M from particularly A is equal to the time taken by the same to reach point M from point B. This By this illustration we can say that this proves that the lightning event simultaneous as observed from point M in ground frame. Okay, so this was the first segment of relativity of simultaneity, where we saw that the events are simultaneous, or you can say the lightning event is simultaneous in ground frame, as it is taking the, you can say, the equal time to reach that particular point. Okay, from the ends. Now, now we will discuss about in the accelerated frame. So our frame number 2, you say train frame, or you say accelerated frame. Okay, now suppose this is a train frame, you can say. Now since it is moving with some velocity v, you can say, or it is accelerating with some acceleration a, again dividing that, just you can say we will get the velocity also by just using the parameter acceleration and time. So I'm just here more concerned about velocity. So just this train frame is you can say accelerating, or you can say it is moving with velocity v also, v. Okay, so here if we will just construct the same, you can setup also, what we'll get here, that suppose this is your back end, we say this is back end. Now back end, okay, this is back end and this is the front end, and suppose this is your midpoint. Initially this is the initial midpoint, so initial midpoint, initial. Okay, now lightning will strike here. Okay, this is very, you can say, easy to understand here, this concept. Here we are not required to prove anything, things are pretty visible, and that lightning strikes at back end. Okay, now also from front end also the same is happening. Now suppose this is a midpoint, so when train is moving in forward direction, then you see this midpoint is also shifting forward, and it is coming, now it is at position M dash after you say some time t. Yeah, now it is at M dash. So what's happening is that as train is moving forward, midpoint is also shifting forward, or it is, you can say, coming closer to front end, and it is you can say at more distance, it is at more distance from back end. So now it's very obvious that this particular lightning will strike at this front end, lightning which is been struck at front end will reach to this particular midpoint in a lesser time than the same from the back end, right? because you see here the very simple concept is there, because here the distance is less. Okay, you see the basic formula, distance is equals to speed into time, right? Now speed is constant for both the cases, so we are just concerned of time. So here the distance is less, you see this is a less distance, this particular distance here, this distance and this particular high distance. So this is less distance, so since distance is less, so time will automatically, it will take less time to reach this particular point m dash. And while the same from back end, it is at higher distance, so it will take a more time to just reach to that particular point. So what we saw here, that the same event of lightning was simultaneous, was happening, or you can say at the same time, in ground frame. But when we are concerned about train frame, or we are concerned about accelerating frame, then the same event is just, you can say, what is not simultaneous, because here from front end it is more inclined, or you can say it is at less distance from front end, so the event will happen first at from event, or you can say the effect of event which is happening at front end will be visible firstly at, or you can say in a less time at m dash, then the same from the back end. So here time taken by lightning strike, or you can say to reach m dash from front end, is less than the same from back end. Got it? So it's very simple and very clear to you all. So just very easy concept it is. So from here we will relate the applications of relativity, that is time dilation, length contraction. Okay. So I hope this particular concept of relativity of simultaneity of events is quite clear to you, because we have taken two frames to understand this. That in one frame, if I have to summarize this, so let me summarize this particular, that there is a note that events which are simultaneous in one frame need not be simultaneous in another frame. This is the actually the, you can say, the core meaning of relativity of simultaneity, that we have discussed this events are simultaneous and all, but the more important is relativity of simultaneity of event means, in particularly in one frame it is simultaneous, but in another frame it is not simultaneous. That is what relativity, relative means comparative, you can say comparatively, or you can say in respect to something. So that is the thing. Okay, so this is one example. But in all these discussion, you have to understand that we are discussing from that frame only. If we are in train frame, we are just dealing with the train frame, that a person is in train frame and is observing this particular event is occurring. Same from the ground frame. But when we are concerned that an event is occurring in train frame and we are observing it from ground frame, then things will differ. Things will differ. Like you can say the result will reverse out. Okay. So if we are observing, suppose there are two frame, ground frame and train frame, and some event is occurring here. Okay, and we are observing that from this observing. So if we are observing this particular event which are occurring here, which is occurring in the train from ground frame, then the things will reverse. Okay, So this is a little more advanced discussion, which is not in our, you can say, context, but you can think on this particular. Just the results gets reversed. Means there you see front and from front end you see from train frame. Now same event is observed from ground frame, then back end will be the major, you can say, deciding factor. So we will not go in quite depth in that, because our main idea or our main, you can say, agenda was to discuss the relativity of simultaneity of event. And one thing also you have to understand is this particular term is also sometimes called Einstein time paradox. So if you see this particular word somewhere, then you must understand that this is actually referring to the relativity of simultaneity of event, nothing more, nothing less. Okay. Now applications of relativity. Okay, so now we will relate our concept of Lorentz transformation, the transformation which we discussed from this particular segment. Okay, in the applications of relativity. Applications of relativity. What are the applications of relativity? There are varied applications. We see it in different you can say context. But the two main contexts which we are going to discuss by relating both of them is your first your time dilation and length contraction, and second is your energy mass equivalence. So I am very sorry for this, because today's lecture, and this will be little lengthy one. Okay, it may reach up to 45-50 minutes, so have patience. Okay, so time dilation and length contraction, energy mass equivalence. From here we will also uh, you can say prove, or you say derive, that kinetic energy is half mv square. Very, you can say, different concepts we are going to discuss. Very interesting these are. Okay, so let's start then. Okay, without any delay. So firstly, time dilation and length contraction. Very beautiful concept and related to the Lorentz transformation. So we discuss about two frames in Lorentz transformation. I'm just making you remember that in one frame we assume that time is t and other is t dash. So that we will use here. T dash is equals to a gamma times t. This gamma is called Lorentz factor, or you say gamma, whatever. Okay. So this gamma is your Lorentz factor. This gamma is given by this. Okay. Where v is the velocity of relative velocity of second frame with respect to first frame we've discussed. Okay. Now main agenda is to understand this concept of time dilation. Okay, so the main agenda is, first of all, time dilation. There is a misconception here. When I studied for first time, I thought that time is reducing, but time is not reducing. Time is same. Relative time is, you can say, changing. What does it mean? Means time, obviously time is not absolute, time is relative, but this these are two types of time. This is a rest time, or this is relative time. Okay, yeah, you can say this is a time at rest, this is the relative time. So this relative time is changing, but this is constant. Okay, same we'll discuss for mass energy equivalence also. So time dilation doesn't mean that in this particular event the time is this, and in this other event the time is different. We are discussing on relative, we are discussing on the relative nature of time, that it seems, more precise word would be seems, that is seems, because we are observing from different frame, we are applying the concept of relativity, so it seems. Okay, time is same, but relative time is changing. This is relative time. Say rest time, no issues. Relative time, this is rest time. Okay, Now I think it's clear. Let's take an example. Moving clock slows down. Moving clock slow down in accelerating frame. What does it mean? That same example. We are taking ground frame and crane frame. Now, if someone is seeing his clock from ground frame or in ground frame, he is reporting suppose 5:30 p.m. IST. And if someone who is there in the, you say, what? Mm, yeah, accelerated frame, suppose train frame. He is reporting the same as, you can say, 5:28, 5:27, like that. Means the delta is there. The delta is there. And that delta, now what is delta t? This is the time difference. But which one will be, you can say, which one will report that it is 5:30 and which one will report 5:20? What will be the deciding factor? Deciding factor will be the velocity, because in the formulation which we did, that t is equals to t naught over root under 1 minus v square by c. In the formulation we did, uh, that velocity factor is very important, because that is the deciding factor. Just take some examples, you will get more clarity. Okay, t dash we used, no issues. Let me change it. No issues. Let me change it. But for that I need, yeah. Okay. So this. Now, when we are concerning about velocity is equals to 0, it is tending to 0, it is at rest, then there is no issue whether you are saying t dash or you are saying t. That's same. That means the same. But when velocity is not 0, it is, you can say, something finite quantity, means less than speed of light also. It is also less than speed of light. Then what we are seeing? That we are just subtracting 1 from this particular quantity. Now this particular quantity, v square over c square. So suppose our c is, our v is, sorry, v is suppose c by 4. Suppose, just for example, not visible. Okay, v is equals to c by 4. Suppose we are taking. So what it will be, c square over 16. Then we will take it c square over 16 over c square, that will 1 by 16, 15 by 16. So 4 by root 15. T dash will be 4 over root 15. 15. Okay. Now this will be around, you can say, this will be around 4 over root 15 will be what? Nearly, you say, this t dash will be greater than t, simply. Then what is time dilation actually? See, when this t dash is greater than t, okay, so that particular clock which we are concerning, that is actually, so this t dash is greater, it means that the time dilation means actually that the result of delta is actually because of this particular t dash, because here when we are writing delta t, that is t dash minus t, because this t dash is coming greater, means you can say, when we are saying that the clock is running slowly, maybe due to battery issue or whatever, clock is running slowly. So the more, you can say, explanation of t dash greater than t, let's discuss. T dash greater than t, it means more time is taken for the same event to occur in t dash frame than t frame. So if more time is taken, time is more taken, it means that, you can say, the rate is reduced. Means, you see, speed, speed, distance over time, we take this as constant. Then if more time is taken, it means speed is less and it slows down. So actually this t dash is an accelerated frame and time is taken more, and this is a moving frame, sorry, moving, I said, ground frame. So then moving clocks, you can say, slow down. But here again, one misconception is there that first of all, what I'm saying accelerating frame, what I'm saying ground frame is relative. Like if we are sitting in train and we are observing the activities which are happening on the ground, then we'll see it as in moving. Okay, anything which is any person who is in that particular frame is at rest with respect to that particular frame. So this the concept of accelerating frame or ground frame is all based on in which you can what is the you can say point of reference, what is means these are relative terms. Okay, in short we can say. So that's we say moving clock slow down, but it doesn't mean that moving, when I'm saying it refers to only accelerated frame. No, we are referring moving, or we are saying that it is you can say frame is accelerating or any frame is moving with respect to particular frame. When we set one particular frame as a point of reference, then we say that in respect to this particular frame is moving. So that is whole you can say concept relative. All concepts are relative here. So that we say here moving clock slow down. So this is your concept of time dilation. Now we will discuss length contraction. Length contraction. What is length contraction actually? To understand this, suppose this is a moving frame or a train frame. Okay, two mirrors are fixed roof side. Okay. In the you can say on the roof and in the ground, or in the you can say the surface of that particular train. Two mirrors are you can say in this way they are aligned at some particular angle also. Now the ray of light will travel. Okay, and then you can say again it will go up and then down. You can say it will, if we see in the respect of this train frame, then what happened that we light a torch and then the brightness is traveling some distance, and brightness is traveling some distance, and then again it is uh, means this distance, if we say t, then this is also t, then that is overall distance is 2d. So it is traveling 2d distance. But with respect to ground frame, with respect to ground frame, what is happening actually? With respect to ground frame, when the person is in train frame, then the velocity of that person with respect to train frame is zero. So he is only observing this particular thing, that is giving him the distance as 2d. But when train is also moving and then it is also covering some d dash distance, then the overall distance which has been seen from ground frame is diagonal distance. And always remember that always remember diagonal distance is greater than the you can say side length distance. Side length distance. So suppose we are concerning of a square, the side is AA, then this is coming as root 2a. So diagonal, this is here that distance of this from ground frame we are observing a diagonal distance, because the direction, if something is you can see event is happening in y direction also, train is moving in x direction also, so the combined motion we are seeing in the diagonal, you can say diagonal path. So that is root 2a. That distance is root 2a. So this root 2a is always greater than a. Always 1.4a is greater than a. So here we also observe that when we are concerning in the moving frame, relative moving frame, then the you can say length contraction is observed. It doesn't mean that length reduced to this. No, there is a just an you can say way of looking at observing at the event uh, through different frames. So length contraction is there. General formulation is like this. You see, right? Same two cases you can write for, and you will see the length contraction is actually happening. But here, this L means different. This L not means different. Okay. What does actually this L? You can even change this formula also to that L dash and this weight. So you can write this L is equals to L dash also, like this also. Because this is your in you can say ground frame, suppose we are measuring this, and this an accelerated frame. Okay. So this little change is there in the formula when we are concerned of time and when we are concerned of the length contraction. Little change is there because here you will same you will put this value, so this length will come greater, and this is actually the case that when the diagonal length is there, then it will be greater than the side length. That's the thing, very simply. So this is the concept of length contraction, that it happens in moving frame. It seems that particularly the distance has contracted, length has contracted, but that's just you can say a way of looking at the thing, way of looking at the implications of relativity. Okay. Now energy mass equivalence. Energy mass equivalence is E is equals to mc square, but when we are concerning of a rest mass, that is m naught, and corresponding to that we will have this particular E naught is equals to m naught c square. This is actually relativistic energy when concerning to the relativistic mass, and this is your rest mass energy, you can say. This is rest mass energy, you see. Relativistic mass energy, sorry. So like this, these are the formulas, but actually this is you can say at rest, this E naught is equals to m naught c square, and this is overall in the relative terms. Okay, so this is, you can say, this E is actually the sum of all energies, you can that. Let's discuss it. So here this particular E is the total energy, which is the sum of E naught and kinetic energy. Okay, now this kinetic energy is E minus E naught. We can write it as m minus m naught c square. Right, now let's discuss about what actually this m naught and m is. So here similarly we can write m is equals to m naught over 1 minus v square by c square. This m is called relativistic mass, and this m naught is called rest mass. Now we can write this as 1 minus v square by c square power minus 1 by 2. Now here you can use an approximation, I think you know, but I'll tell you. So whenever we see here that 1 minus x power n, we can write it as 1 minus nx, when you can say here that when the magnitude of this x is very much less than 1, then we can write this particular approximation, and here we will use that 1 minus v square by c square minus 1 by 2, so 1 plus half of v square by c square. Okay, so this is the concept when we use, when this mod of x here is v square by c square, this is very much less than 1. Okay, because obviously the velocity will be very less. Often you can say an object which is moving, it may move with 50 kilometer per hour, for 40 kilometer per hour, and whatever, but it will be very less than the square of the velocity of speed of light. So here also v square is very much less than c square. Magnitude you can take. Okay, no issues. So now we will discuss here that k is equals to m minus m naught c square. Now m we can write m naught, and we can write it as 1 minus, oh wait, 1 minus, yeah, 1 plus, sorry, 1 plus half v square by c square minus m naught into c square. Now this m naught minus m naught will get cancelled, and you will get half m naught v square as your kinetic energy. Okay, the c square gets cancelled, is m naught minus m naught gets cancelled. Kinetic energy is coming at half m naught v square. So from here you can also derive the quantity, you can derive the value of kinetic energy when we assume that this v is very much less than c, hence v square is also very much less than c square. Then we are getting this approximated value. Okay, half m naught v square. Okay, so this is the way you can reach to this particular result. Okay, so this was your energy mass equivalence concept. Okay, so actually whatever with the whatever formula we use in you can say mathematics or physics, they follow a certain pattern, and when we observe that pattern, then we just name it as name it like this, kinetic energy half mv square or potential energy mg, and then that's making a very complex pattern in mathematics. And then we just see how it is working, we observe it, and then we come into the conclusion of this particular kinetic energy is equals to half m naught v square. Okay, so this is your formula for kinetic energy. You can write k or you can write ke also. So this was your second application of relativity, that is energy mass equivalence, which we discussed. And even you can take some cases also, like to understand this formula better. Suppose we take the case of photon. Okay, so this formula is there and we are taking the case of photon. So taking the case of photon, so mass of photon is not actually zero. What actually zero is m naught of photon, that is your rest mass of photon. So when we will look at this formula, what actually we are getting, what we say mass of photon is zero, but actually it is not zero, m naught of photon is zero. And now the photon is actually traveling with the speed of light, so v is tending to c. So then we will see that this particular quantity will also be zero, and this is also zero around and around. So this mass will be undefined. This mass will be undefined. So your actually the mass of photon is not defined as per the actual, you can see 0 by 0 form it is forming, so it is not defined. There are seven indeterminate form, or you can say undefined, or you can say indeterminate. Both mean the same almost. So indeterminate or undefined. So actually it is undefined and indeterminate. But what we say mass of photon is zero, generally speaking, that is actually the rest mass of photon, that is m naught. Okay, and in same way you can relate it to energy also. E is equals to E naught by or E is equals to gamma E naught, where gamma is 1 by root under v square, 1 minus v square by c square. Okay, so this was your applications on relativity and relativity of simultaneity of event, which we discussed earlier. Okay, so with this I think our today's goal is completed. So with this our today's goal is completed, and in the next lecture, that will be more or less the last lecture, lecture number 10, we will discuss about intro to 4D system and concept of light. Interesting concept, we will discuss about it. This lecture will be around of 20, 25 minutes tentatively. Okay, the exact date of when this lecture will come will I'll tell you in the community post, but this will be the topic, intro to 4D system and concept of light cone. So around 20 to 25 minutes tentatively in light cone concept, we will take 10-15 minutes, and around 10 minutes in the intro to 4D system. Okay, and with this our more or less foundation level is done. Okay, so okay, then we should leave, and please do revise all the concepts which we have discussed, and please try to write all these on your own. What we discussed, Lorentz transformation, you should derive on your own also. That will give you more clarity. Okay, so this was your lecture number 9, and now in next lecture we'll discuss about these topics. So do practice, you can say Lorentz derivation, Lorentz transformation. Okay, and revise all these concepts, and you can try to get that same result. Okay, kinetic energy equal to half mv square using this particular, that E is equals to gamma times E naught, which we discussed. You can use this also, you will get the same result, m naught. Okay, so practice this, means we can use this particular also, that we know that E is equals to E naught is equals to m naught c square. So from that you can write E minus E naught, and then you can try. Okay, a little brief I am giving you here. You can write like this, gamma minus 1 m naught c square. Just write guess this gamma, and then you will again get this particular result. Okay, that is kinetic energy here. This is your kinetic energy. E minus E naught is kinetic energy. Okay, so all the best. And in next lecture we will discuss about those topics, and we will complete this series. Okay, then next we'll discuss about quantum physics, and that we'll discuss later on community post. Okay. Okay, thank you. So let me show you the thank you slide. So thank you so much for joining me in this session. This session was a little lengthy. It is reaching to 45 minutes, 46 minutes, but no issues. This was a very important lecture to understand the applications of relativity and to understand the simultaneity of events. Okay, so thank you. Bye bye. Take care. And exiting from this video in 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10.